Hey, everybody.
Hello.
Hey, Dr. McGrath.
Hello.
Hello.
Hi. Hello.
All right, let's get started. Okay, so this week we actually are going to do some real statistics, right? We're not just going to be looking at vocabulary and things like that. Grading status, I sent out the email. You guys should have hopefully gotten it and saw that I've already graded your week 1 homework. So if you have any questions on that, just let me know and we'll take care of it. And then this week, we're all about measures of center. So if you haven't already seen my videos on it, or you aren't already familiar with that, the 3 main measures of center are the mean, the median, and the mode. The mean is what everybody is probably already familiar with because it's the average. It's pretty simple. The median is that that big cement barrier that goes down the middle of the highway that you slam into at 3 o'clock in the morning because you fall asleep. And because it's in the middle of the highway, that'll help you remember that it's also in the middle of your data, right? So the median is the middle point of your data. Obviously, you have to order your data from smallest to biggest. Otherwise, anything could be the middle of it, right? So they call that another measure of center because obviously it's the center of your data. And you can actually report it as kind of a pseudo average. And normally we will report the median instead of the mean whenever we have large outliers, right? And outliers are numerical pieces of data that are extremely different from everybody else. So for instance, let's say you wanted to report back the average salary of the workers at your company. Well, if you just took the average salary of all of the regular workers, that would be fine. But if you took the average salary of all the employees, including, like the CEO who makes, $1.5 million a year, then the average is no longer going to be accurate because that really high paid CEO is going to skew the data. It's going to pull the mean further up, to bigger numbers because of that $1.5 million. So in that case, you would report the median and you would say, hey, 50% of everybody who works at this company makes this amount or less. And so it becomes a little bit more accurate kind of dart to hit the middle of your data, right? It becomes a little bit more of an accurate measure of center than the mean would be when you have outliers. Now, you normally report both so people can see, okay, here's the average. I understand average. Here's the median. I understand that to be 50% or fewer, or 50% or that number or smaller. And when I can look at the difference between those numbers, I can see the influence from an outlier. And then the mode, of course, is just the value or values that show up the most frequently in your data. So here are some examples. Data set A. Where is the median for this one? Right? What's the middle value for this one? We got 9 pieces of data. So anybody want to guess what the median is?
7.
Yeah, the second 7 right here. This one right here, because that's the 5th number, right? You got 4 below and 4 above.
Right.
Okay. So now down here, we have an even set of numbers, right? 1, 2, 3, 4, 5, 6, 7, 8. So what's the median for this one?
7.5.
Very good, Susan. Yeah, because when you have an even number, the median lands right in the middle and you have 50% below and 50% above, and you have to average those 2 numbers. So you get 7.5. If this was 7 and this one was 9, then of course the average would be 8, right? So it's always just the average of the 2 numbers that lands in between. Very good. Okay, so I'm not going to beat a dead horse and go through 2 more examples. I think it's pretty obvious that if it's an even number of things, it lands in between them and you average those 2. And if it's an odd number of things, it's going to land on a number. And of course, that number is the true median. Now you can also figure out medians if you are given frequency distributions, right? So a frequency distribution says, hey, here's your data value on the left. In this case, they call it score. And on the right-hand side, this is how many times that data value showed up. So in your set of data, you had 2 people that scored 1, 5 people scored 2, 4 people scored 3, 2 people scored 4, and 1 person scored 5. I might have said that wrong. 4 scored 3, 2 scored 4, 1 scored 5. So you can find the median very easily by adding up your total frequencies, right? If I add up my total frequencies, this is 7 plus 4 is 11, 12, 13. There's 14 total pieces of data. So I know that the mean is going to be, the median is going to be in between the 7th and 8th number. Well, the 7th number is a 2, right? Because 2 plus 5 is 7. So the 7th number is a 2. The 8th number is a 3. So the median's right in between the 2, and the median is going to be 2.5. You could also, of course, list everything out, right? And then count up and see that, okay, there's 7 is and then in between is the 2 and the 3. So that's how to define it from frequency data. And then, of course, here's another example. The same thing, right? You can add up all the frequencies and go, okay, there's 40. So the median is going to be between the 20th and the 21st, right? So 5 plus 8 is 13, plus 9 is 22, right? So the 20th and the 21st are in this class. So the median is basically in this class. And what normally happens with classes, you could either report it as a median class and say the median class is 40 to 50, or you could say the median is approximately 45, because what you would do is you would just take the middle of this class and then report that as the median. It would be the same thing if you want to try and find the average of this set of data, which of course I would recommend never doing. But if this was the only data you had and you didn't actually have the real, original data, then the best you could do would be to treat all of these classes as their midpoints. So it would be something similar to the example on the left, except you would now take this class and you would treat it as 25. And you would say, I've got 5 25s, and then I've got 8 35s, and I've got 9 45s, and so on and so forth. Then you could take each of those values, multiply them by their frequencies, add all that together, divide by 40, and that's your average. It's the same over here. If you took 1 times 2 plus 2 times 5 plus 3 times 4 plus 4 times 2 plus 5 times 1, added all that together, and then divided by the total frequency, which we saw was 14, that will give you the mean. And that'll actually be an accurate mean, because when you're doing this number times its frequency, right? When you do 1 times 2, that's really just adding 1 twice. And when you do 2 times 5, that's just adding 5 2s, right? So when you do this whole multiply, and then add them together, it's just a shortcut for adding all 14 numbers. And then you go ahead and divide by 14, and that's how you get the mean when you're dealing with frequency data. Okay, cross tabulations. This is something that you guys have to be able to do in the mini project for sure. And I think it also comes up in the homework, but it definitely comes up in the mini project, and students mess this up all the time. So please pay attention. Cross tabulations are only done with frequency counts. So that means we only do cross tabulations with non-numerical data. So nominal level data, right? Or what's called qualitative level data, data that just describes things, usually data that are words. And then all you can do with that data is count how many you have, i.e. frequency counts. So in the example here, we have 2 variables. We have the class rank variable that has 4 different values: freshman, sophomore, junior, and senior. So in your data set, each student is going to have a class rank, and they're going to be ranked with one of those 4 words, right? So that's called qualitative data or nominal level data, because all it does is it names a characteristic, right? It tells you what rank they are, class rank. Now, even if instead of freshman, sophomore, junior, and senior, you put 1, 2, 3, and 4 for first year, second year, third year, and fourth year, even though those are numbers, they are still considered nominal level data, because somebody who's a sophomore, a 2, isn't twice as much as a freshman, right? They're definitely they're technically rank, so they would be one step above nominal. They'd be ordinal level data, because there's an order to them, right? There's an obvious order that a sophomore is, after a freshman and a junior is after a sophomore and so on and so forth. But they still wouldn't be numbers that you could like average or do anything like that. They're not ratio level numbers. They're not in the quantitative family. So data comes in two families. There's quantitative stuff, i.e. numbers that we can play around and compute things. And there's qualitative stuff, which just describe a quality. And the only math you can do with those is frequency counts. Even if qualitative data is represented by numbers, you still can't mess with those numbers numerically, right? You can't calculate anything from them. And people do this all the time when they shouldn't. A very common example of numbers that are technically not quantitative are Likert scales, right? Strongly disagree to strongly agree, that could be on a 5-point scale. So instead of using the words strongly disagree, disagree, neutral, agree, and strongly agree, they could just use the numbers 1, 2, 3, 4, and 5. And then you would have all this data where, okay, they gave me a 3 on this question, a 2 on this question, a 1 on this question, a 5 on that question, and so on and so forth. So one of your variables would be, the answers to a particular question. You would have all these numbers from the respondents, everything from 1 to 5. Well, people will falsely take those numbers and they'll calculate a mean, and they'll say, hey, the average of this question was a 2.5. Well, that's total crap. You can't do that because those numbers are not what we call ratio level numbers. A 3 is not 3 times as big as a 1. It's just more than a 1, right? They were just neutral rather than strongly disagreeing. So those numbers would be considered ordinal because there's an order to them, right? A 5 is bigger than a 4, and a 4 is bigger than a 3, and so on and so forth. There's an order to them, but they don't have magnitude. A 5 is not exactly 1 bigger than a 4. A 4 is not exactly twice as big as a 2, because you don't say, well, if somebody agrees, then they have twice as much something than somebody who disagrees, right? If you disagree, you're a 2, and if you agree, you're a 4. So how is a 4 twice as much of a 2? Twice as much as what? Twice as much agreeness? It doesn't make sense, right? You can't give them magnitude. You can't do math with them. All you can really do is report frequencies, but people will often do means, medians, and modes of ordinal level data when they shouldn't. You can do a mode, because a mode still just tells you the most frequently occurring number. That's fine. Just like you could do a mode with these words and say, hey, sophomore came up more than any other, right? Or junior came up more than any other. But you can't do medians, you can't do means, you can't do any kind of numerical computations. So when you're stuck with this kind of data, this qualitative level data, and qualitative level data can either be nominal, where all it does is name something, or it could be ordinal, where there's an order to it. Those are kind of the two. But in either case, when you have that kind of data, all you can do is do frequency counts. And when you have frequency counts, you can put them in this nice little cross tabulation table. And what it does is it shows how many things you have across 2 different categories. So the first category being the horizontals, here being class rank, and the second category being the verticals is where they live, right? They either live off campus or on campus. So you can see you had a grand total of 231 students who lived off campus. You had a grand total of 157 students who lived on campus, for a grand total of 388 total students that, took this survey or you got data from in some way. And then these little totals over here, of course, tell you how many freshmen, sophomore, juniors, and seniors you have. So obviously freshmen would be the mode there, right? Because you have more freshmen than anything else. Just like off campus would be the mode between these two, because you have more people living off campus. But you can look at the cross tabulation and say, hey, I have 37 freshmen who live off campus, and 100 of my freshmen live on campus, and so on and so forth. So that's what a cross tabulation table does, is it basically just gives you all the frequency counts for your data and then classifies them 2 ways. So it gives you the frequency counts for 1 variable vertically and 1 variable horizontally. Any questions on the cross tabulation table? Okay, then we will move on. Next, we can talk about measures of dispersion, right? So first we talked about measures of center, which was the mean, the median, and the mode. Now we're going to move on to talk about measures of dispersion, or sometimes called measures of spread. And these are things that describe how spread out your data is. The most common measure of spread or measure of dispersion is the standard deviation. I think everybody's probably heard the term standard deviation, and you know that it has something to do with how spread out your data is. If you have a very small standard deviation, everything is clumped together and your curve is going to be really tall and skinny. If you have a large standard deviation, then everything is spread out and your curve is going to be shorter and wider. That's basically visually what a standard deviation does. Numerically, what a standard deviation computes is roughly, now this is not exactly what a standard deviation does, but in order to wrap your head around it, really understand what a standard deviation means, is it roughly gives you the average distance from the mean. So for instance, if we look at test scores, let's say, you all took a test and it was a normal test that, ranged from 0 to 100. And let's say the class average was 80 and the standard deviation was 5. Then that would mean on average, each student's score was 5 points away from the mean of 80. Now, obviously, all of you didn't score 5 points away from 80. That just happens to be the average difference, right? Some people scored above 80, some people scored below 80, but on average, they were 5 points away from the mean. That's roughly what a standard deviation does. What it really does is it gives you percentages. So we'll talk about this later, but if you go one standard deviation in both directions on a normal curve, this is only when your data is normal. So when you have this nice little pretty bell curve on a normal curve, if you go one standard deviation in both directions, i.e. the red area, this line in the middle, this black line in the middle represents the mean, the median, and the mode, right? Because the frequency is represented by the heights. So this is obviously the tallest place, so that's the mode. And you can see that it's symmetrical. So you have exactly half of your data below and half of your data above. So this becomes the median. And then just because of the way the normal curve works and because it's symmetrical, right? So all of these values that are a certain amount above the mean are being offset by all of the exact mirror images that are below it. So you end up getting the mean is the same thing. So the mean, median, mode are all exactly the same when you have a perfectly normal set of data. Now, you never have a perfectly normal set of data in the real world. But you can get things that are pretty damn close. But in any case, once you have the center line, this is the mean. If you go one standard deviation in both directions, so the red part here, that is going to be roughly, not exactly, but pretty close to 68% of your data. So let me go up here and draw. I'll do it in red. This right here is 68% of your data. Now, if you go out 2 standard deviations in both directions, right? So you get all of the green stuff. So you can see that everything, red and green put together, right? All of that stuff put together, that's 2 standard deviations, 1, 2, right? You can see how these are all the same width because they're the same distance, right? Standard deviation of 5. So this is 5 points and then another 5 points. If we had a standard deviation of 5, you get the idea. Well, if we go out 2 standard deviations both directions, then that's roughly, not exactly, but pretty damn close to 95% of your data. And then if we go 3 standard deviations, right? So we go all the way out to the third one and gather up all of this data, that's going to be 99.7%. Again, not precisely, but pretty darn close. So you can see that the tails, the 2 little tails, the white bits on each end, have very little data in them, right? You've got 99.7, damn near all of your data is within 3 standard deviations of the mean when you have a normal distribution. Now, this is still a normal distribution. It's just a normal distribution with a smaller standard deviation, but the rules are still the same. You would still have 68, 95, and 99.7. That's called the empirical rule, and that'll come up later. But I figured since we had a nice little pretty picture, we could talk about it here. So that's really what the standard deviation gives us, is it helps us figure out how far we have to go in each direction in order to capture these percentages.
May I ask a question?
Of course, Wiley, go for it.
What do you do if that bell is skewed one way or the other?
Great question. So if it's skewed one way or the other, then the empirical rule just no longer applies. And we can no longer say we have 68, 95, and 99.7. However, we can still calculate percentages using calculus, but luckily we have statistical tools that do it for us. So even
Okay.
if your data isn't normal, you can still run a statistical analysis and figure out how much data is between certain points. You know, like if you want to just say within one standard deviation in both directions, you could do that, or whatever the question is. You could always figure out how much data is in your curve, even when it's skewed. You just can't do it as easily and as cleanly as you can when it's perfectly normal.
What can you use the standard deviation with? Is it used in calculations or?
Yes, it's used in a lot of calculations. So to do a lot of these statistical calculations by hand requires a standard deviation.
Okay.
So for instance, later on, we'll see that we can compute what are called z-scores. Z-scores are based on standard deviation. So you need a standard deviation to do that. Confidence intervals. If you're going to calculate a confidence interval, be able to say, I'm 95% confident that the mean is between blank and blank. You need the standard deviation to compute that, right? So just about any statistical result is calculated using the standard deviation.
Okay. Thank you.
Yep, of course.
Dr. McBride,
Yes.
and this is probably a silly question. When a lot of my exams, when I look at the scores, it usually ends up being like a bimodal curve.
Yeah, sure.
Yeah. Is there a similar way to calculate like outliers and stuff like that from each one of those modes? Does it break out like this, or is that just really, really awful math?
No. That's a common misconception. Just because you have two modes doesn't change what an outlier is. An outlier is still based on how far away it is from the center of your data. So it's really not so much from the modes, it's still basically being calculated from the center of your data, i.e. The median, and really more specifically the quartiles that come off the median. So even with two modes, bimodal data, or skewed data, or whatever it happens to be, outliers are still really just a measurement from how far they are from center.
Okay, thank you.
Yeah. And then Amy, as far as it goes for other things, like you would still calculate the mean the same, the median the same. It's still based on all of the data. It just so happens you have two modes. The standard deviation would be calculated the same. And just like Wiley's question, the standard deviation still tells you overall how spread out your data is, but it no longer gives you these simple percentages, but it would be used to calculate things. Okay, anything else? Okay, so here's some examples of small and large standard deviations. Some small standard deviations would come from prices of cars, as long as you're looking at the same model of new cars. Because if you're looking at the exact same model, right? So you're looking at a Ford Mustang. Sure, a Ford Mustang can come with all sorts of different options that are going to change the price, but they're not going to change the price a lot relative to the price. Like the starting price is going to be 40 grand. You get a bunch of options. You could get up to 50 grand, or maybe strip some things off and get it down to 30 grand, but still it's not a huge difference from the mean, comparatively speaking. And then the same would be for like heights of 30-year-olds, because by the time we're all 30, we should have stopped growing. So we should all be roughly the same height. Now, obviously there are tall people and short people and people in between, but there's not going to be a huge variation. They're all going to be close together, versus if you looked at the heights of 7th graders, well, some of them are growing faster than others, right? Some have already had growth spurts and some haven't. So you're going to get a much bigger spread of heights. Now, the average height of a 7th grader is obviously going to be less than the average height of an adult. And that has nothing to do with standard deviation. Standard deviation has everything to do with how they're spread out, right? And then the same would go if you looked at prices of the same model of used cars, because now once they're used, there's a much bigger variation in how much they cost, because, mileage and, accident damage and things like that. So you can have things with a really big mean, right? A really large number for the mean, and it could still have a really small standard deviation. You could also have things with really, really small numbers that have a really large standard deviation, right? So there is some correlation to it, but it's not a strict one-to-one correlation. And because of that, we can calculate what's called a coefficient of variation. And what it does is it helps to kind of level the playing field. Because of course, big numbers will have bigger standard deviations because they're based on those numbers. And when I say bigger, I mean, for instance, the standard deviation of cars is going to be bigger than the standard deviation of heights, because we're talking about things in tens of thousands versus we're talking about things in, tens, if we're talking about inches, right? So height in inches is going to be between, like 50 and 80 inches, much smaller numbers than 40,000, 50,000, 60,000 up to 100,000, for cars. So of course, whatever this standard deviation is going to be, even if it's a very tight set of numbers, it's going to be on the scale of thousands, which is much bigger than on the scale of tens, right? So it's not fair to compare apples to oranges and say, hey, this group has a larger standard deviation than this group, so it's more spread out. Well, not necessarily, because it could come from data values that are just larger. And the example they use here is weights of mice and weights of elephants, right? We're talking about mice in grams and elephants in tons, right? So obviously the standard deviation for elephant weights is going to be a much bigger number than the standard deviation for the weights of mice, but that doesn't mean that elephant weights are more spread out. They just come from a data set with larger numbers. So in order to be able to compare those two data sets more equitably, we do what's called a coefficient of variation. And you take the standard deviation and you divide it by its mean. So it now becomes basically a percentage of the mean, right? When you divide something by something, it becomes a percentage of it, right? So if it was twice as big as the mean, when you divide by the mean, you would get an answer of 2, which is a percentage would be 200%, right? If it was half the size of the mean, when you divide it by the mean, you get 0.5 and it would be 50%, right? So when you do fractions, you're basically getting percentages. And so by doing that, you're able to compare these two different things, right? So for instance, with the mice example, they had an average of 9.3 grams and a standard deviation of 2.4 grams. Over here, the elephants had an average weight of 2.2 tons and a standard deviation of 1 ton. And you're like, oh, well, how do I compare 2.4 grams to 1 ton, right? Which one's more spread out? Well, if you do the coefficient of variation and do this nice little ratio, you see that this standard deviation is roughly 25% of the mean, whereas this standard deviation is almost 50, right? It's 45.5% of the mean. So the elephants are more spread out, right? Their data is wider. That standard deviation of 1 actually represents a more spread out data set than a standard deviation of 2.4 because of the difference in the numbers. And that's what the coefficient of variation gives us, is it allows us basically to compare apples and oranges. And you can see here that, like I said, they take that ratio and they multiply it by 100 so that you can report it as percentages, just because human beings understand percentages more than anything else, right? So for instance, with this data, if I said 25.8% versus 45.5%, that would be even more meaningful to the average person than to say 0.258 and 0.455. You don't have to do that, and it's not wrong if you don't. It's just, it's a more, it's a clearer way of describing the data to the general public. Okay, those are all of the statistical things that you're going to need to compute for this week's homework, and a lot of the stuff that you need to do for the mini project as well. And like I said, if you watch my videos on measures of center, measures of dispersion, and measures of relative standing, you'll get even more information on all this stuff and more. So by all means, check those out if you have some more questions on the statistics involved. Now, that's all I have for you guys as far as the quote unquote lecture part of today is. Do you have any specific questions from the homework? Would you like to see how to do some of this stuff in SAS, Excel, those kinds of things? So what do you guys want to do next?
Yes, I have a question.
Yes.
So I know on the homework it was asking, let me log back into them. It was asking, construct a pie chart or whatever.
Sure.
How do we, okay, so let me make sure that I understand this. I was able to figure out how to get my data onto SAS. So I
Excellent.
did that. So you know how it says practice question 3.1? Is that where the data is going to be with that? Because I know when I transported the data over, it was like 3 point something.
Yes, I mean, for 3.1, you should be using data 3.1. So for instance, if you go to SAS Studio and you have 3.1 loaded, right? I'm going to go ahead and close this out and start fresh. So you basically have a screen that looks like this. If you grab this and drag it or just double click on it, either way, what it does is it just loads it in this window. But remember, that hasn't loaded it into SAS. It's just loaded it into the window. You have to click the little running man and actually run it. And when you see this little table-y thing at the bottom, that lets you know that your data has been loaded into SAS. I always like to click on the output data tab so I can actually see my data. This is my data set. This is everything that I have for this, simple set of data for question 1. Now, like you said, question 1 says construct a pie chart, construct a bar chart, then construct a pie chart for percentages, and then, a pie chart and a bar chart for percentages. And then they ask you which of the 4 charts is most informative. Okay. Well, now that we've loaded the data, we can go back to our SAS stuff, and down here at tasks and utilities, we can go to graph. And under graph, we can choose pie chart and double click that. And just like before, double clicking it, all it does is it loads it into the window where it can do things for you if you run it. The first thing you have to do is make sure that you grab your data. And so
Okay. How
you
did
gotta-
you get graph on that? Like,
how to get what?
Task.
You have to go to
I'm-
task and utilities, and then under tasks, then you have graph, and you have all the graphic
Oh, okay.
stuff.
Got it.
Now, when you run your data, it will tell you where it saves it, and it saves it in the work library, and then it gives it the name import. And if I open a second set of data, it will just be called import 1, and the next set of data will be import 2 and import 3, and so on and so forth. Every time you shut down SAS and reopen it, this starts all over again, and your first set of data will always be import. Now, you could change it if you want to. You could come in here and you could change the name and call it, 3-1, but it doesn't like that, right? So how about 3.1 and hit save? And now that's my data set. So now when I go to choose my data set, you click this little table view, and you can scroll down, and it's still showing it as import, which is weird. Let me try reloading it.
So once we
Yeah, it looks like it's back to import. So maybe the change just didn't take place. But in any case, I don't recommend changing it because you're just adding complexity.
I watched one of the videos where it taught us how to change it, and I kind of already did that part.
Okay, well, that's fine. If you want to change the name, that's fine. But it's not necessary. As long as your data is loaded, that's all that matters. You click on here and you go and find it, double click on there, which loads your data. Once your data is loaded, you can then add in your variables. Now, why is it sending me, it doesn't like this? So let's try this again. Place it. Okay, let's close this. Let's open it again.
Mine's is not doing it either. I don't know if anybody else is.
There we
working
go.
on it.
Okay. So sometimes you just have to close it out and reopen it. It just gets glitchy. So I closed it out and I reopened it, and now it no longer has that little exclamation point here. So it's actually seeing the data as work.import. And when I click on this, I can add things. So obviously my category, right? Let's say I choose program for my category, and then I run this. Look what's going to happen. I just get this pie chart. Now, why is it showing 1 for each of these when my data has, 612 for this and 852? Why am I just getting 1s for all of these?
Is it because you didn't run it or something? I don't know.
No, it's because when you run a pie chart, SAS goes to the data and says, all right, how many times does nat.def show up in my data set? Shows up once. How many times does this one show up? Showed up once, right? It's counting how many times this variable, I chose program as my counting variable. So it's only going to come up once. That's why you have to come down here, and instead of measure its frequency, you have to measure it on a variable. And say, now, instead of going in and looking at how many times each of these words show up in my data set, tell me what their variable value is, i.e. their expenditure variable. And if I run that, now it shows the proper numbers and the proper sizes for all the pie charts, because it's now computing the pie chart based on 852 out of the total, and so on and so forth. And then if I want to do percentages, right, all you have to do is change this variable to the percent variable and run it again. And now it lists it as percentages. You'll notice that the pies don't change shape, because they still have the same relative size, right? If this was a quarter of your data, then the pie is going to be a quarter, whether you list it as a percentage or whether you list it as its number of things. So the sizes of the pies aren't going to change. All that's going to change is you're going to get percentages instead of raw numbers. And that's how you do a pie chart.
Dr. McBride,
Yes, Amy.
is there an easier way to get the pie chart from SAS into our Word document? Because I was just basically hitting that little arrow and it was pulling it up into a screen, and then using my snipping tool and
Yeah.
And then,
I mean,
is that the way to do it?
you can do that, but you can bypass the whole opening in a new browser tab. By opening it in a new browser tab, it just gives you a cleaner thing. You can just use the snipping tool, right now from this window, right? So just leave it where it is and hit new, and then just come in here and.
If it's a chart, you can also right click on it and say copy image.
Yes.
Okay, thank you.
If it's a
knew there had to
table,
be a
you-
quicker way.
Right. If it's a table, that doesn't work, but
Right. Yeah.
Yeah.
So I find that it's easiest to always just use the snipping tool. Sometimes right click works, sometimes it doesn't. I don't like having to worry about when does it work and when does it not work. I'm just always going to do the snipping tool, because then you can go into Word, right, and just go to wherever you want this thing and hit Control V, and there it is. And then you can click on it and you can, resize it and do whatever you got to do.
And you
So
would prefer everything on one page, like,
I want everything in one document. It doesn't have to be on one page.
okay.
So your homework can be multiple pages. That's fine. I just want you to upload, or if you want review, send me just one file. I don't want multiple files. I don't want a Word document and an Excel. Like if you're doing work in Excel and you want to show me your Excel stuff, then copy and paste it into your Word document. Don't send me a separate Excel file. And the same goes when you submit it. Don't submit a Word document and an Excel document. You have to take all of your Excel stuff and copy and paste it into Word and just have one document.
Regarding the
Brian?
showing your work, do you want us to put a write-up of how we get there, or it's not needed in cases like this?
Yeah, for simple things like graphs and stuff, there's really no work to show. In fact, any kind of output you're going to get from SAS, you don't have to show any work. You can literally just clip it and paste it. The only time I would want to see quote unquote work is if you do any programming in Excel. Now, you're probably not going to program anything this week, but starting next week, you might use some of those programs that I showed you guys that is in the Google Drive. Let's see. Franklin. 807, SAS stuff, and the how-to guide. So for instance, starting, well, you could use it if you want to do mode. So let's say you wanted to get the proper mode and you use this code in SAS. Then take a screenshot of your output and then click on code. Sorry, not there. Code here. Take a little screenshot or just copy it and paste it. It's even the easiest way, right? You can just highlight it all and do Control-C, Control-V right into the Word doc. I kind of like that because it stuff will then wrap if this is too long to fit on your page, so it'll actually wrap around rather than if you copy and paste it, then of course everything shrinks down in order to fit and then the words get really small and it's hard to read. So if you were playing around with code, you can copy and paste the code only if you're having problems and you need my help right during review. But as far as your answers are concerned and showing your work, it's just the output. All I need to see is the output. And please, guys, please do not take a screenshot of the whole damn screen, because then this gets too small for me to read. Take a screenshot of just the specific little square that has the output in it and put that in your Word document. Okay, great.
Thank you.
Anything else? Okay, so that's pie chart. Obviously, bar chart is pretty similar. You just double click on bar chart to load that, right? You pick your data. You pick your category just like before. Again, if we pick program and then run it as is, we're going to get the same thing as before, where everything has a frequency of 1. And you, oh, darn it, because that's just picking up each variable as once. So instead, we have to measure it, right? So instead of measuring it on how many times, we measure it on a variable. And the variable we're going to use is the expenditure variable. And now when we run it, we get bars that reflect how many we have in each category. And then, of course, if you change it to the percentage one and run it, all that's going to change is over here on the left-hand side. Instead of them being numbers, they're now percentages. Okay, so those are your 4 things that you have to do for question 1, and then you just have to pick which one you think is the most informative and why, right? So that would be the only type of question where you would have to wax rhapsodic, right? Where you'd actually have to talk about it. Is you can't just say, oh, I'm going to pick this one. You have to say why, right? Which of the 4 is most informative and why do you think so? These you're just, here's my chart, bing, here's my pie chart, here's my bar chart, right? You don't have to talk about those at all. It's just when they have questions where they ask for your opinions that you have to give an opinion and justify it. You always have to justify your opinion, guys. Always. In this class, really, and in life in general, but definitely, in your thesis or your dissertation, you're going to have to justify all your opinions. So you better get used to it here. All right. What else? Any other homework questions or SAS questions or technology questions?
I have a question.
Yes.
So when you give your opinion, even if you justify it based on what you think, of course you would submit documentation to justify what you're saying, what your recommendation. Is there a right or wrong answer?
For opinion questions, no, right? Everybody is you're all welcome to your own opinions. I personally think sometimes stronger arguments can be made for different opinions, but that doesn't mean that I'm going to mark off because you chose one of the weaker ones, as long as you justify your opinion, right? So I'm not going to tell you which of these 4 I think is the best, but let's just say you chose the bar chart with percentages. You'd say, okay, I think the bar chart that shows percentages is the most informative because human beings tend to understand percentages more than numbers, right? And it tells me more to know that this category is 25% of the data rather than just telling me it's $562 billion, right? It's that kind of thing. But then somebody else might argue, well, you know what? I'd rather know exactly how much money is being spent. So the bar chart with numbers rather than the bar chart with percentages is more informative because it tells me, holy crap, there's $821 billion being spent in this category rather than just telling me it's 22% of the budget, right? So you could argue either one as long as you argue it. That's all that I'm looking for.
Okay, thank you.
Yep. And Latanya, you don't have to like go find some source that, says human beings like percentages more, if those types of things can't be sourced, right? You get where I'm going with that?
I do.
Okay. Anything else?
Dr. McBride,
Yes, Pamela.
could you show me one more time how in SAS, okay, so we click on the 3.1, how we get that to be our source to run the data?
Sure. So let me clean everything out, start fresh.
Did she just ask you to go back and explain how you got how you put it into like put the data in there?
Yes.
Okay, got it.
So under server files and folders, somewhere in here, you should have a file folder with all of your data sets. Whatever data set you want to work with, you simply double click it. And then it
Okay.
shows up over here. But it's not ready for you to analyze until you click the little run symbol. I call it the running
Okay.
man. Once
Okay.
you do that, now it's loaded in SAS. You'll see that it's now in import one. So now if you want to go do something, so like now let's say we want to, instead of do a graph, let's run some summary statistics. Let's do mean, median, mode, and that kind of thing. So we come down here to summary statistics. We double click on that. And just, it doesn't matter what you double click on, it's going to look pretty much the same, where the first thing it's going to ask for is your data. So you need to go and choose the data. Now our data is now in import one. So I got to choose import one, because if I left it on import, nothing would show up because there's nothing there anymore because I closed that data set out. Now, our analysis variables just basically says, when we're talking about summary statistics, it's which variable do you want to run these summary stats on? So I click add, and you'll notice that before, maybe you didn't notice, but before when we were running graphs, all three of our data were listed. All three of our variables were listed. Let me get the graph back up here so you can see the pie chart. So when we go to the category for the pie chart, it shows all three of our data values. Next to program is a little a, which means it's recognizing this data as qualitative. A letter being, words, because under program, it just had, national defense, social security, it had words. But expenditure and percent, it has the 1, 2, 3 because it recognizes those as numbers, and it says I can run analyses, statistical analyses on numbers. However, when I go to summary stats and I click on add, it only lists expenditure and percent because it's smart enough to know that it can't run summary statistics on words. So it doesn't even list that variable. So I'm going to double click on expenditure and say I want to run summary statistics on the expenditure variable. Now you might want to remind yourself that the expenditure variable is literally just these 5 numbers, right? So it's just going to give us summary statistics on those 5 numbers. So once we've done that, then we can go to options where we can tell it what we want to run. I want the mean. I want the standard deviation. I don't want these. I want the median. I don't need number of observations. I can click on additional. I can get all sorts of other things that you guys are going to need, in other homework stuffs. I can do percentiles, which you might need, again, for other homework questions. You can go to plots and you can get a histogram and a box plot and all sorts of fun stuff. Details, you can do degrees of freedom. You can just play around all day long. But for now, we're just going to do some basic statistics and then run. And there it is. It's hard to see. I'll make it a little bigger. Ooh, a little too big. There's your mean. There's your standard deviation. There's your median. And if you wanted to put this into the Word document, you would just snip this little table and stick it in your Word document. And that, like if the question said, give you, calculate the mean, standard deviation, and median for your data, then there it is. So
should we sort the data first, or it's okay just to leave it like that, and then later if we need to sort it for something else, then do it at that point?
You never need to sort the data for anything, because like if you want to find the median, it kind of sorts it for you and finds the median that way. The only time you would ever want to sort the data would be if you wanted to visually inspect it for some reason. And then if that was the case, I would say it's much easier to sort it in Excel. Just open the Excel file and play with that one.
Okay.
Yeah. Okay. So are we all set on how to load data and how to run it in various simple programs?
Yes, thank you.
Of course. Any other questions? Even specific ones from the homework? You struggling with any of these that you want to talk about?
Dr. McBride,
Yes,
sorry to
Amy.
keep bugging. I did the first two questions, and the second question, the 3.4.
Yep.
I was only able to figure it out because I watched your video, which showed the step-by-steps what to do.
Sure.
So I don't know. For some reason, the histogram was giving me trouble because, you know, I used the data from the Excel and then changing the number of bins and all of that. Would you mind, I hate
Yeah.
to say walk through those steps, but would you walk through those steps?
Yeah, the histogram is it's ugly if you don't play around with it, which is why I gave you guys a code down here to make better looking histograms, which you can use if you really want to play around with it. It's not required, but if you want to play around and get a better looking histogram, that's really unfortunately what you have to do. Now, as far as this is concerned, for this question, all you have to do is load your data 3.4. You'll see that now this time, because I've done it multiple times, it's going to put it in import 2. I always like to click on my output just to see what I have. I've got fluoride, bins, frequency, relative frequency. Okay, so that's what's going on here. The bins frequency and relative frequency was something that I created in Excel and put this here for you guys. If you went and found this data file from the schools pages, right? If you went to just the class website and got it that way, it's not going to have that extra stuff. You only get the extra stuff if you get the data files from our Google Drive. Just an FYI. You're always better off taking the files from my Google Drive because I've done all sorts of extra formatting and helpful things to the data files for you that you don't have to do yourself. Okay, it's loaded, right? It's an import 2. Now we go to task utilities. The first thing, you know, we need to do is determine the range and then divide the range by 7, right, to get the number of subintervals. So that would be under summary statistics. So if we go to summary statistics and we just change our data now, come down here and we double click on import 2, and then we add the fluoride data and we run this, we're not going to get the range, right? Because we turned that off. So we have to go to the options here and we have to do range. And then now run it. And again, hard to see, but there's my range, 0.33. Then if we divide that by 7, we get a class width of close to 0.05. So it says, go ahead and round it, and we get a class width of 0.05, and they want us to start with 0.705, which is where in our data, these classes come from. See how it starts at 0.705. Again, I'll make it bigger so you can see it. 0.705. And then it's a class width of 0.05, right? 0.05. So that's why this goes from 705 to 755. And then if I add 0.05, right, it gets to 0.805. So these are the classes that come from basically what it tells you to do in part B. Now, as far as a histogram is concerned, under graph, we've got histogram. So we click on histogram. We need to make sure we have the right data. It just defaulted to our last set of import 2, which is great. That's all. We don't need to change that. We need to put in our fluoride, right? And just always just run it once to see what happens. All right, so that's the original thing that we get from fluoride, which is, you know, fine, but it's not great. Part C says compute relative frequencies for each class interval and construct a relative frequency histogram. Okay, so now we need to do a relative frequency histogram, which means we have to do it based on the relative frequencies. So instead of fluoride, pick relative frequencies and run that one. There's our relative frequency histogram. Again, looks horrible. And that's because this is doing it on the actual data and not relative frequencies based on what SAS wants to do, right? So there's two ways to do this, because it says, note that the frequency and relative frequency histograms for these data have the same shape. Well, no, they don't. This looks totally different than the last one we did, because this one is based on our relative frequency variable, whereas what they're expecting you to do is just under fluoride, right? So I'll run it again so you can remember this is what it looks like for fluoride. But if we change it, see, instead of percent, we can do proportion, which is what relative frequency is, and run it. Then we get the same thing. That's what they mean by a relative frequency histogram. A relative frequency means how many things you have relative to the total, right? So if you have 5 things out of 100, then that class, right, that group of numbers represents 5% of your data, and the little height would be at 5%. So relative frequency is just another way of saying proportion. Okay. Percent is pretty much the same thing as well, right? That's a relative frequency as percents. So percents of proportion, same darn thing. And then if you just did count, again, all that changes is the vertical axis. The shape doesn't change, because instead of this being represented as a percentage, it's just saying, oh, this category had 2 things, this category had 8 things, this category had 8 things, this one had 6, and this one had 1. Okay, so that's just the difference between frequencies. These are frequency counts because it tells you exactly how many you have. And then relative frequency is just percent or proportion. They mean the same thing. As you can see, percent is usually the default. And then that's a relative frequency histogram. Okay, now it says, note that they're the same. Yep, great. It says it wants you to have, right, 7 intervals, and we only have 5. So if we go to appearance and bins, and we tell it to put in 7 bins, this is one way to get 7 pieces. There's a really low one there, and then 2, 3, 4, 5, 6, 7. So that would be basically what you would get, kind of the easiest, most standard way of having 7 intervals, because in part B it says divide the range by 7. So it seems like it wants, 7 bins. When you don't specify it, what happens is SAS basically just chooses the number of bins that it thinks gives you kind of the best looking graph. So it thinks this is the most informative looking graph. If you really wanted to make it look good, you would have to go in and change the code, right? And so if you click on the code button, it always brings up what the code is. And here's the standard code. If you want to change this, you can't change it as it sits. You have to click the edit button. When you click the edit button, it creates a copy of the code, and you'll notice that it's no longer the histogram. It's called program 1, because now you can futz with it. You can change things. And if we go up here and we look at this, if we wanted the thing to look better, what we need is this code here, because it tells it where to start for the bins, how wide the bins are, and then it gives you a much prettier histogram. And then if you really want to get fancy down here, it's an even better way to make it look really good. So just copy all of this down to where it says run, right? This part just tells you that it's also going to give you relative frequency. So just Control C and come up here, highlight all your data, and just do Control V to replace it. And now all you need to do is change this to make sure it represents where your data is, right? And if you look at your old stuff, the data here was an import 2. So just make this import 2 and run it and see what you get. So here are all kind of like descriptive things that you get from that code. It does all sorts of analyses. It gives you quartiles and that kind of funny stuff that we'll deal with later. And then here's your pretty little histogram. So here's the histogram with 7 things, starts at 0.705 like it's supposed to. Looks like it's flipping us off, right? And then here it is as relative frequency, right? So this one is just frequency, right? So here's frequency counts. And then here's relative frequency counts. These are percentages. It would be better if it listed as percentages rather than numbers, because this makes you think, oh God, there's 7 of these. No, it's 7%. Okay. And then here's just some more stuff that it gives you for the relative frequency. A bunch of extra crap you don't need. But there are the 2 graphs that are really super pretty using code. All I wanted to point out is that if you want to start playing around with code, it's not that difficult, especially if you have, somebody already did the code for you. Then all you ever need to change is where your data is located. And then of course you would need to change the variable name if your variable was called something else, right? So if you want to use this with another data set and you had a different variable, then you would just change it from fluoride to whatever that variable was called. And then you could run this, on your dissertation data. Okay. So does that answer your question for 3.4?
Yes, thank you. Thank you.
Of course.
Yeah, I don't have the pretty version. I've got the less pretty version.
Which is totally fine, guys.
Okay.
And let me be perfectly clear with this. You do not ever have to code in this class. Okay, you can do everything just the standard, normal, easy way, and that is totally fine. The code is just there for those of you that want to challenge yourself and try and learn SAS a little bit more than just the basics. Now, I will warn you that there are certain things that SAS will not do properly, and you will get the wrong number or the wrong result if you don't use code. And I always put those in here, for instance, for doing the modes, right? So those little stars, right, tells you that SAS, along with most technologies, does not report multiple modes if they exist. SAS reports the smallest of the modes if you have more than one mode. If you do this in Excel, it will do the same thing. If you do it in a TI graphing calculator, it will do the same thing. Now, in Excel, there is a way to get it to report multiple modes. So you could always do it that way if you needed to report multiple modes. And in SAS, you have to use coding. Now, you might ask yourself, well, how the hell do I know if I have multiple modes or not if I just run it and it just reports something? You don't. Because if you just run it, it's just going to report a mode. And if you have multiple modes, it's just going to give you the smallest one you've got. The only way to know if you actually have multiple modes is to either run the code that finds them, run the Excel version that finds them, or open the data in Excel, sort it, as Eduardo had talked about, and then visually look through your data to see if there's more than one mode, because now that it's sorted, you can see, oh, I've got 4 of these and 4 of those. Ah, crap, I've got 2 modes. It's that kind of thing. Okay. So just keep that in mind. That's one of the things that it does not do correctly. And there is a question that asks you to find modes. And there are multiple modes in that question. I can't remember if it's in the homework or the mini project. Let me look really quick. Oh, it's in the homework. So question 24, there are multiple modes. So if you run 24 in SAS, it's just going to give you one mode and you're going to get it wrong. So you need to figure out how to find multiple modes for question 24. Okay, any last questions before we go? All right, guys, thanks for showing up. Remember, Thursday will be basically just all Q&A. If you still have questions about how to do things and you want me to quote unquote lecture on something like explain standard deviation again, I'm more than happy to do that. So don't feel like you can't ask those types of questions. I'm just saying that the theme or the major idea for Thursday is that between now and then you will try all of the homework questions. And then on Thursday, you can ask for help with any of them that are giving you troubles. And then hopefully by the end of Thursday's meet session, you will have figured everything out and you don't even need to send it to me for review because you know you've got everything good to go because you asked your questions and you can just submit it. Okay? All right. See you guys Thursday.
Bye-bye. Thank you.
Yep.
Bye.
Good night.